back to the second lecture in module 2 on finite element method. In the previous lecture we had an introduction to finite element and weighted residual formulation. We will next take up variational formulation, finite element shape functions and numerical integration, and then applications to scalar transport problem in the next lecture. So, let us have a recap of what we did in the previous lecture. We discussed the background and the attractive features of finite element method. We also discussed the basic finite element methodology, and we discussed one particular type of finite element formulation which is most popular one, which is called weighted residual formulation. We looked at the general formulation of weighted residual method and the weak form which we can obtain from here, and what are the major types of schemes which can result from the generic weighted residual formulation. We then applied a particular variety of weighted residual formulation which is used in finite element formulation called Galerkin finite element for Poisson problems. And today's lecture we would focus primarily on finite element shape functions and numerical integration, but we would also include a variational formulation, a very brief look at this particular methodology, and then we will start off with finite element shape functions specifically for one dimensional problems and two dimensional problems in detail, and then we will have a look at numerical evaluation of the integrals which occur in finite element analysis. Now, let us have a look at variational principle. Yesterday while looking at the basics of finite element method, we said the starting point was energy minimization for mechanics problems. So, if we can minimize potential energy, so potential energy is a function of what is referred to as a functional, and if that can be minimized, then that would lead us to a stable state of the system, that is to say our solution. So, this is what happens for a certain class of problems in physics. It is possible for us to define a scalar quantity, for example potential energy in mechanics, whose stationarity leads to the solution of the problem. That is to say, we have to reach either an extrema, it could be a minima or a maxima. This is what we mean by stationarity here. So, formally we can define this variational principle as the specification of a scalar functional pi which is defined by an integral. So, pi is integral over the domain f x comma u comma del u by del x plus del u by del y comma so on and so forth d omega. So, here f is a operator, x is a spatial coordinate, and u is the dependent variable which we want to solve for, plus we might have a surface integral, that is integral over gamma which is the boundary of the domain omega, it another functional g which depends on x, u and the derivatives of u. So, this integral leads to a scalar quantity which we popularly call a functional, and the popular symbol to use is capital pi. Now, we seek solution of our continuum problem u by finding out a function u which will make this functional pi stationary with respect to arbitrary changes in delta u. So, that is what we can say, that arbitrary variations in delta u which leads to delta pi is equal to 0. If we can find such an u, that u would represent the solution of our problem. Now, if we can find a variational principle, then it is straightforward to establish an integral form suitable for finite element analysis. We have already got that integral definition of pi, and that is what we can use in our finite element methodology. However, please note that in practice it is very difficult to obtain an expression for operators f and g from the differential equation of the problem. So, normally the way we had seen when we derived our conservation equations, we derived it either in integral form, but that did not correspond to a variational principle, and thereby after we obtained a differential form. So, what we would have most of the time is a differential equation, and looking at that differential equation, it is very difficult for us to formulate or to come up with the forms for the operators f and g, except when our differential equation involves what we call a linear operator, that is what we say linear differential equations. So, in the case of linear differential equation, suppose we had L was our differential operator, and if it were self adjoint operator in the differential equation Lu plus f is equal to 0. So, in that case you can look at your maths textbook and it will tell you that in such situations we can obtain this function or operator f which is given by u times Lu minus 2f, and functional capital pi can be defined as pi is equal to integral omega of f d omega, we substitute for f, that is u multiplied by Lu minus 2f. So, now this is our scalar functional, we minimize it and thereby we would have our finite element formulation. So, now let us have a look at the variational finite element formulation. We have got the functional pi, so that is the one which provides the integral form. For instance, this is similar to the weak form which we have derived earlier using weighted residual formulation. So, we have already got something similar to a weak form for finite element formulation, and all that we would require is now we would require stationarity of pi with respect to each nodal value, which should lead us to the discrete algebraic system. And if pi is quadratic, then the preceding step results in a linear system k is equal to b, which will have some nice properties. But before that, let us have a look at how we reach at this stage. So, variational finite element formulation. Suppose we have got our functional pi defined. Okay. So, our functional is pi, and then we will use our finite element approximation. So, suppose functional pi exists, that is we have got a scalar functional pi defined as a function operator f times x u of x and so on d omega. Now, what we want in finite element analysis, we seek an approximate solution, solution u tilde, that is we will approximate our u of x by u tilde x, and this u tilde x is defined in terms of our interpolation functions, that is n I, which depend on the spatial coordinates, and the discrete nodal values. So, u tilde x is summation over I of n I x into u I, and our task is now to determine u I. So, functions, note that the functions n I x are known, and we have to determine discrete nodal values u I to get the approximate solution, finite element solution of our problem. Okay, now we want to find out a solution, or we seek a solution which would make pi stationary. That is what we seek, is that stationarity of pi functional pi requires that delta of pi, this is equal to 0. Now, any variation in delta that can be expressed now in terms of, so delta pi, this is given by summation over I del pi over del ui delta ui, because that is the way we have expressed our approximate solution. Our approximate solution depends on these unknown discrete parameters ui. So, that is how the small change in pi can be represented as this. Now, this is what we want to set as 0. Okay. So, this, let us call this equation as 3, and 3 must hold for arbitrary variation delta ui for each ui. So, that is possible only if the multiplier which we had in this summation is identically 0. Delta ui's, they could be arbitrary for each I, and if we assume that looks for some i's this del pi by del ui is positive, for some it is negative. So, that assumption does not hold good. Okay. Though it is possible for us to argue that there could be certain variation for certain values of I which are positive, for others it is negative. So, we get a summation is equal to 0, but that will not hold good for an arbitrary variation in each of ui's. So, that is why what we would require that for stationarity of the functional for arbitrary variations in ui, these derivatives delta pi over delta ui, this should be 0 for each I, and this is what gives us our discrete algebraic equations for discrete algebraic equations which we seek as a part of our finite element formulation. And of course, those discrete equations would be in terms of the elemental integrals, and we need to evaluate those integrals to get the final discrete system. So, the intermediate steps would be similar to what we earlier looked at in weighted residual analysis. One final discrete system would be K u is equal to B, where K is system matrix, U is the vector of unknown quantities, and B is our right hand side. So, this is in a nutshell the basic variational finite element formulation. Now, there are some beautiful features of this variational finite element formulation, and one of these beautiful features is that if pi is quadratic, then the system of equations which we get from finite element formulation K u is equal to B, this K is symmetric and positive definite. So, that gives us specific advantages in terms of solving this system. In fact, for many of the problems what has been observed in mechanics is that if there is a variational principle in existence, variational finite element formulation invariably results in a symmetric system matrix. This also yet another feature in such situations, that is to say that if we have a problem for which a variational formulation is possible, that is to say we can find a functional, in such cases even if we employ a Galerkin finite element formulation, that would also result in a symmetric system. So, that is the reason why nowadays instead of trying to search and formulate the variational functional for a problem, most of the time we prefer to go with Galerkin finite element formulation, firm in the knowledge that if there were a variational formulation which we were seeking to obtain a symmetric system, that we would anyway get by using our Galerkin finite element formulation. So, we just had a look at one form. There are many generalizations of these variational formulations available in the literature, which are called constrained variational principles. Some of them are based on Lagrange multipliers and penalty functions. For details, please have a look at any standard finite element book. For instance, you can have a look at the book by Jinkwitz or Reddy. We will give the full reference of these books towards the end of the lecture. There is yet another category of somewhat similar to variational formulation, wherein we can construct a functional based on least squares approach. Now, I have just given the sketch of this approach here, because this is the one which is used occasionally in finite element analysis of fluid problems. So, what we can do is, instead of trying to search for a variational principle for a given partial differential equation LU is equal to F, if we substitute for U or approximate solution, we will get the residual R. Okay. And now, let us define a functional pi bar, which is given by R square d omega. Okay. So, R is our residual. What we have here is square up that residual, and to get a solution we want to minimize that residual. That is the reason why this is called least squares formulation. So, for details, once again I would encourage you to have a look at the book by Jinkwitz. Now, let us come back to the finite element shape functions. In today's lecture, we are going to focus on some most commonly used polynomial shape functions, though if you look into the finite element books and literatures, there are a variety of finite element shape functions which have been derived for different physical problems, for different scenarios. For instance, in solid mechanics, we have got a set of functions which are used for plates and shells and so on, but we would focus primarily on the most popular shape functions of polynomial type. And please remember, the shape functions in finite element analysis would depend on dimensionality of the problem, whether we are dealing with one dimensional problem or two dimensional problem or three dimensional problem. In each case, we will have a different shape function. They will also depend on type of elements which are used for discretization, whether our elements permit quadratic variation, linear variation and so on, or say for instance we have used in solid mechanics, we want to use a plate element or a shell element and so on. So, what type of element we have used, that also dictates the form of our shape function. Now, the shape functions must satisfy certain continuity requirements. Now, this continuity requirement will depend on the type of formulation which we have used, which will specify that order to which our shape functions must be differentiable. So, that is what we saw in previous lecture, that weak form results in a lower continuity requirements on our shape functions. So, depending on, let us say if you want to use strong form or weak form finite element formulation, and the order of differential operators in PDE, these two factors will govern the continuity requirements on the shape functions. But there are some basic properties which our shape functions must satisfy. So, two basic fundamental properties. The first one is called partition of unity, that is, at any point in our domain. So, if we sum up all the shape functions for that element, so sigma k is equal to 1 to n k at any point in that element, it should sum up to 1. So, that is, this property is called partition of unity. The next is Kronecker delta property, that is, they simply say that our shape functions say ni at node xk should be equal to delta ik. So, if I pertains to that particular node, if I is equal to k, the shape function should take a value unity there, otherwise it should evaluate to 0 at that elemental node. Now, let us have a look at some standard shape functions. We will first discuss the shape functions for one dimensional element. We will concentrate on two types, 2 node linear elements and 3 node quadratic elements. For description, let us switch over to our board. One dimensional shape functions. Now, it is customary to define these shape functions in terms of what we call local variables or natural coordinates. So, shape functions are normally defined in terms of a local coordinate, which is usually called natural coordinate. So, how would you define the natural coordinate for a one dimensional element? So, let us say we have got a one dimensional element, the extent of this element in x direction, suppose the length of this element is L. Now, the origin of this x coordinate could be anywhere. So, for each finite element, if we define our shape function in terms of x, the definitions should change. But if you introduce this natural coordinate, we can have identical definition for the shape function in each of those elements. So, now how do we define the natural coordinate? We will define the origin of natural coordinate at the centroid, that is the middle point of the element xc. So, xc is the midpoint of our finite element, and we would define, let us use the symbol xi to denote our natural coordinate. So, this natural coordinate xi is defined as x minus xc twice of it divided by L. Now, please remember that now xc is the middle point. So, at the midpoint, the way we have defined, it should evaluate to 0. What happens to the extreme ends? So, in terms of xi, if you draw the same element, let us draw it again. So, our xi coordinates are 0, minus 1, plus 1. So, at the extreme right end, it is very easy to see, this part is L by 2. So, x minus xc is L by 2, twice of that is L divided by L, that will give us a value plus 1, and same holds. Similarly, we can see why the natural coordinate of the node A should be minus 1. So, this is our definition of natural coordinate for one dimensional elements. Now, depending on the number of nodes, we can specify what type of polynomial variations or shape functions we would like to have. So, now let us have a look at two cases. First is what we call two node linear element. So, we will start the numbering from left. The leftmost node is numbered as 1 and the rightmost node is numbered as 2, and the way we have defined our coordinate system, the middle of the element, that is where origin of xi lies. Node 1 has got coordinate minus 1 and node 2 has got coordinate, so xi is equal to plus 1, this is xi is equal to minus 1. And associated shape functions, in this case there will be two shape functions. Shape functions n1, the subscript 1 says that now this is associated with the node 1, this would be defined as 1 by 2 into 1 minus xi, and n2 is given by 1 by 2 into 1 plus xi. Now, you can easily verify the two properties which we have mandated the shape functions should have. Okay. At any any arbitrary point xi in the element, what happens to this summation of these safe functions? We have got 1 by 2 1 minus xi plus 1 by 2 1 plus xi, which gives us 1. So, these shape functions, they do satisfy. So, thus n1 and n2 do represent a partition of unity. Similarly, can you verify the Kronecker delta property? Let us see what happens to Kronecker delta property. N1 at, let us call the coordinates of node 1 as xi1, n1 xi1, where xi1 is minus 1. What is this? This is 1 by 2 into 1 minus minus 1, which is equal to 1. And what will happen if we evaluate n1 at xi2 is equal to plus 1? This is 1 by 2 1 minus 1 is equal to 0. Now, let us have a look at one more one dimensional element. Let us call it quadratic three node element. Now, if you have got this 3 node element, let's draw a element diagram. This is center point, which is the origin of our local coordinate system xi. The leftmost node is numbered as 1. The central node, we will number it as 2. The center node is that xi2 is equal to 0, xi1 is equal to minus 1, and the rightmost node we will number as 3. So, xi3 is equal to plus 1. Now, the shape functions are n1 xi, this is given as 1 by 2 xi into xi minus 1. The shape function a link to the middle node, this is given by 1 minus xi 1 plus xi, and the last one n3 xi, that is given as 1 by 2 xi plus 1 into xi. So, these are the shape functions for quadratic one dimensional elements. Now, do they satisfy the two properties which we require, that is our partition of unity? So, let us sum them up. Sigma n I xi, I is equal to 1 to 3, and what do we get? 1 by 2 xi square minus 1 by 2 plus 1 minus xi square plus 1 by 2 xi square plus xi by 2. Xi by 2 gets cancelled. Now, these two xi square, these ones will again cancel. So, what we are left with is now this sigma I ni xi is equal to 1. So, thus these shape functions, they do satisfy this partition of unity property. They also satisfy Kronecker delta property, which we can easily say, for instance, our n1 at minus 1, this is equal to 1, but if you evaluate n1 at 0, it is 0. Similarly, n1 at plus 1 is also equal to 0. The same holds good with n2, n2 at minus 1 is 0, n2 at the node point 2 is equal to 1, and n2 at the node point 3 is equal to 0. Similarly, our n3 minus 1 is equal to 0, n3 0 is also 0, but n3 at the node 3, that is n3 xi plus 1 is equal to 1. So, thus these shape functions our ni's also satisfy Kronecker delta property. Next, let us have a look at some of the standard shape functions for two-dimensional elements. In two dimensions, we can have either rectangular elements. In the polynomial class, we have got two families, Lagrange family and serendipity family. We will have a look at what are these two families separately, and then triangular elements. So, two-dimensional elements. We will first look at rectangular elements. So, we are using the word rectangular. These shape functions can also be used for the curvilinear elements which have got four sides by using what we call isoparametric mapping, or these can they also can be used for the quadrilaterals of arbitrary type. But for the basic definitions, let us stick to that rectangle shape, and here again we need to define our natural coordinates. We need to introduce now two natural coordinates xi and eta. So, if you are looking at our xy coordinate system, let us say we have got a rectangular element. The centroid of this element, that is what would be chosen as the origin of our natural coordinate system. So, the one local coordinate parallel to x, that is what we will call as xi, the one parallel to y direction, that would be called eta 0 0. Okay. And their definition is very similar to what we had defined earlier for the one dimensional case, that if the extents of this element, the length of this rectangular element in x direction is Lx and its length in y direction is Ly, we can easily see the definition of this, xi would be defined as twice of x minus xc divided by Lx, and eta would be defined as twice of y minus yc divided by Ly. So, this is the basic definition of our natural coordinates for a rectangular element. And now, in terms of these coordinates, we will define the shape functions for rectangular elements. First, we will have a look at the elements of Lagrange family. Why we call them elements of Lagrange family is because of simple reason that the shape functions are defined in terms of Lagrange polynomials. Okay, that is to say our typical Lagrange polynomial, let us call it as Lkn for a one dimensional variable xi. This is defined as the product of I is equal to 0 to n, I not equal to k, x minus xi divided by xik minus xi. So, this is a definition of a Lagrange polynomial. Now, in terms of Lagrange polynomial, the shape functions are defined. So, shape functions for a quadratic element, a quadrilateral or rectangular element can be defined in terms of L k xi. That is for example, for a node A, or let us use this index alpha, the shape function n of alpha that can be represented as n capital I capital J, where this capital I capital J can be used to represent that which side, left side or right side, we can assign the integer indices for these ones. Similarly, we can also assign the integer indices for the bottom side and the top side. And now this Nij, in fact, it represents or it is expressed in terms of these Lagrange polynomials Ni n xi Lj m eta, where this n and m would tell us that how many number of divisions we have got in that particular direction. To make it clear, put it more clearly, let us define linear elements. So, linear Lagrangian element. Now, this linear Lagrangian element would have basically 4 nodes at each corner of this rectangle, and the shape function Na can be represented as 1 by 4 of 1 plus xia into xi, 1 plus eta a into eta, where xia, eta a are coordinates of node A. So, what you can easily see that these are basically the products of the shape functions in one dimension. So, what we had the shape function in one dimension, 1 by 2, 1 plus minus xi into xi. So, that is say 1 plus or minus xi. So, that is what we will have here, that xia and eta a, they can take the values plus 1 or minus 1. Okay. So, the shape functions for the linear Lagrangian element, they are basically product of corresponding linear shape, one dimensional shape functions. The same thing can happen, in fact we will have to repeat exactly the same way if you take higher order elements, quadratic or cubic, we take the corresponding one dimensional shape functions in the two directions, multiply them, and we will get the shape functions for higher order Lagrangian elements. For details you can see the book by Jankovic. I would just like to illustrate one point that relates to the placement of nodes. In the case of linear elements, yes, we had 4 nodes at the 4 vertices, but if you take quadratic element, so this is our linear rectangular element. If you take quadratic rectangular element of Lagrangian type, we will have 3 nodes on each side. Plus we will have one node which coincides with the centroid. So this becomes, this is a 9 node element. Similarly, if you want to have cubic one, that will have many more interior nodes. So this is cubic element. So if we do not want these interior nodes, we can go for what we call quadrilateral elements, quadrilateral or rectangular elements of serendipity family. The linear one, of course, did not have any node in the middle, so we do not have to worry about the linear node. But if you go for the quadratic one, say for instance, or cubic ones, we can obtain the shape functions, or we can define the shape function in such a way that we do not need any interior node. So this is our quadratic element of serendipity family. The same way we can define our cubic element of the serendipity family. So for details, for detailed description, please see the book of Jankovic et al. Okay. Now the shape functions are for this element would differ depending on where the node is located. So suppose we are dealing with the corner nodes, these are defined in the same way as we had earlier done with slight modification. So this is 1 by 4 1 plus xia into xi into 1 plus eta a into eta and plus a modifier term, so multiplied by modifier term xi a xi plus eta a eta minus 1. And if we had mid sides nodes, the nodes which are sitting at the centers of each of the sides. So, mid side nodes is slightly different version. So, if we have, let us say, the node which sits on the sites defined by or whose xi coordinate is 0. So, then the shape function is defined as 1 by 2 1 minus xi square 1 plus eta times eta a, and if is eta I coordinate is 0, which will correspond to two mid side nodes. So, in this case the shape functions n a would be 1 by 2 1 minus eta square 1 plus xi a. So, in this way you can find the details of the shape functions for other higher order elements, and for the further description we will take up the next family of elements, the triangular elements, and numerical integration in our next lecture.